So now that we've talked about semaphores, let's in some sense take a step back and talk about an even more primitive synchronizer in Java called the ReentrantLock. And you'll see this is important for a variety of things that you'll need to know about. But it's also a good example of some core fundamental principles of synchronization. So in this part of the lesson, we're going to talk about the concept of mutual exclusion, which you can read about more here. So let's start by talking about mutual exclusion locks, which are the means to achieve mutual exclusion in a variety of different programming languages. So a mutual exclusion lock, which is sometimes called a mutex, is used to define a so-called critical section. So of course that kind of begs the question, what is a critical section? So a critical section is a block of code or a region of code where only one thread at a time can be running in. So that's the important concept, is only one thing in there at a time. And typically the way that works is a thread comes along, it wants to enter the critical section, it is going to acquire some kind of mutex lock, which then lets it into the critical section. Think of this like a doorway. And then once it's inside the critical section, it can run, and it can access whatever the protected resources are, protected fields or state or whatever you want to call them, inside the critical section. Meanwhile, any other threads that come along that want to access the critical section have to wait. They're kept at bay. And the reason for doing that, of course, is so that they don't corrupt the shared resources, this thing, via multiple concurrent operations. If multiple operations, if multiple threads were able to run within the critical section, then race conditions could occur. They could smash into these data structures and muck them up. Remember, a race condition is a problem that arises when a program, piece of code, depends on a sequence or timing, sequence meaning the order, the sequence or timing of threads for it to operate properly. And there are lots and lots and lots and lots and lots of examples of things that work that way. Almost anything that involves any shared fields that can be called and manipulated by multiple threads, if not properly protected through critical sections and mutexes or some other means, will end up being corrupted and race conditions will occur. When a thread is finished, it leaves the critical section. So when this thread is done, it goes ahead and leaves through this door, if you will. And then that allows some other thread, a thread, to acquire the lock and enter the critical section and start to run. So now it's running, whereas these threads are still waiting. Under the hood, a mutex is typically implemented in hardware via so-called atomic operations. We've talked a little bit about these. Remember, an atomic operation is something that appears to occur instantaneously and will typically change the state of the system or have no side effect at all if it doesn't run. So think about transporter beams when you think about asynchronous, or when you think about atomic operations. Under the hood, the atomic operations are implemented by things in Java like the compare and swap methods that are part of the so-called unsafe class. We talked about these briefly earlier, and I gave you an overview of kind of how they worked. We don't have to know all the details, but be aware that this is how it works under the hood. And the persons who are responsible for making this work are mercifully not us. They are the JVM or Java executor or execution environment implementers. So let's talk quickly about a human known use of mutual exclusion locks. You've all probably dealt with this if you've ever flown in an airplane. So this is a simple example. The airplane restroom protocol. If you've ever flown in a plane, you've seen this before undoubtedly. And so the way it works is as follows. You come along, you need to use the restroom, and if the sign says vacant, then you can enter the restroom. And when you're in, you shut the door and that locks it, or you lock it. So now it's occupied. And if anybody else comes along who wants to use the restroom, they have to wait. So they're like the threads. The restroom in this case is the shared resource. And when you leave, you unlock the door and leave, and then someone else can go ahead and go in and follow the same protocol. So this is another good example of something that's fully bracketed. The person, or thread, who locks the door must be the same as the person who unlocks. Unless there's an emergency and you have to come and break the door down or something like that, right? Which actually is not too far-fetched from the computer world, because if your thread goes berserk, you sometimes have to open up a task manager or some other means and kill the whole thing, right? That's kind of the equivalent of breaking the door down. But under normal operation, that's not how it behaves. OK, so that's the end of the ReentrantLock discussion, the first part. So let's now go ahead and talk about the second part of the ReentrantLock lesson. And here, now that we've talked about sort of the concept of mutual exclusion and critical sections and so on, we're going to talk about how the Java ReentrantLock gives you the means to provide mutual exclusion to concurrent programs. Once again, you can see that there's a lot of methods. There's even more methods than I haven't shown here, but these are some of the core ones. So let's first talk about the overview of ReentrantLock. So basically, this is the most simple and powerful. It seems strange to say those two things in the same phrase, but it's really the simplest and most powerful way of providing mutual exclusion to concurrent Java programs. Maybe rather than simple, I should say the most efficient way to do it. And as you can see here, we have ReentrantLock, and then it implements a bunch of things. And one of the things that the ReentrantLock implements is lock. So the lock interface is what provides the methods that ReentrantLock will implement. It does other stuff too, but that's the core set of things it's going to do. If you take a look at the lock interface, you'll see two things. First, you'll see what the methods are that it implements, and they're very simple. It's like lock and unlock and try lock and so on. But it also has a really nice description of some of the properties of Java synchronizers. So I recommend you take a look at this link and read this, because it gives you a good insight about how they're designed and why they do what they do and why you need them and so on. And also some of the properties they provide in terms of atomicity and visibility and so on. ReentrantLock, like Semaphore before, implements the bridge pattern. And the point is to decouple the interface from the implementation. So you have a fixed interface with the operations like lock and unlock. And then the bridge pattern is used to delegate those calls to either the fair version or the non-fair version. And then the bulk of the implementation logic actually lives up here in the framework that is provided by the abstract queued synchronizer. So this, again, is almost identical to what we looked at before. So we have a sync object here that's a field. This thing will then go ahead and extend abstract queued synchronizer. So that's the framework where the bulk of this logic resides. And that's used to provide FIFO wait queues. You'll see why I need those. Those, of course, are what's being used under the hood to do things like implement the specific notification pattern. So they do it for you. Your assignment will have you do it to learn how it works, but they do it for you if you use that implementation. Once again, you optionally implement fair or non-fair lock acquisition models based on the values that are provided here. So if you give the value fair, then it'll go ahead and select the fair sync if it's true. Otherwise, it selects non-fair sync. And then by default, they also have one that gives you non-fair sync. Once again, just like with semaphores, the non-fair implementation is way, way faster because it uses hardware optimization. So only use the fair version if you really need it, like if you're implementing something where you have to give FIFO ordering. The ReentrantLock, in some ways, looks an awful lot like the mechanisms that are provided by Java's built-in monitor objects. So if you're familiar with built-in monitor objects, when you have, say, synchronized either on a method or synchronized on an object, like synchronize this or synchronize whatever, then that will acquire the lock or block acquiring the lock. And then when the close curly brace of that block or method is reached, it'll unlock the lock. So they're similar. And we'll talk more about built-in monitor objects here probably on Wednesday. But there's also a lot more stuff that ReentrantLock provides. And that's because the synchronized statements and the synchronized methods in Java built-in monitor objects are very, very limited. And they have a number of deficiencies that are overcome by the mechanisms that are available in ReentrantLock. So, for example, one thing that you can do with a ReentrantLock is you can lock interruptibly, which means I'll try to get this lock, but if the thread is interrupted, I will return. In contrast, Java synchronized methods and blocks or statements are not interruptible. So once you've committed yourself to trying to access something, trying to get access to a synchronized block or synchronized statement or synchronized method in Java built-in monitor objects, you are committed. You are not leaving there easily because you cannot be interrupted. Really weird, bizarre semantics, by the way, and one reason why people tend not to use synchronized a whole lot if it matters. Then you also have these cool try-lock mechanisms. And try-lock is also something that is not provided by the built-in monitor object synchronized statements, synchronized keyword. Try-lock will acquire the lock only if it's not currently held, and try-lock with a timeout, the second version, acquires the lock if the current amount of time has elapsed. It'll wait up to the current, it'll wait for the designated time to elapse before it'll return. So it lets you do basically timed acquisition. And in contrast, the mechanisms that are available in Java built-in monitor objects don't provide timing at all. And I should also mention that there's a wait operation on a monitor object that has bizarre semantics. So this is much, much better than what you get out of the box there. Another interesting thing about a ReentrantLock is it supports so-called recursive mutex semantics. So you can take a look here, reentrant mutex or recursive mutex is the same thing. And this is basically the way it works under the hood. The thread that holds the lock, the mutex, the ReentrantLock, can reacquire it without deadlocking on itself. So if something is a recursive lock or a recursive mutex or a reentrant mutex or whatever, it can reacquire the lock without blocking on itself if it owns it. And the way it works is it keeps track of a count called the hold count. And it starts out where if you acquire the lock and you become the owner, then the hold count is equal to 1. And if you come back around again and try to reacquire it by saying locked, then rather than blocking, it simply increments the hold count by 1 and allows you to continue. So this is very useful in certain circumstances. The downside with recursive semantics is that it's a little bit slower than non-recursive semantics. And the reason for that has to do with the fact that you've got to have some additional software mechanisms and some additional synchronizers in there to handle the recursive semantics. So you can't simply do it with hardware instructions alone. And for that reason, in many implementations, many operating systems and so on, not Java, but in many other environments like POSIX, POSIX locks, they give you a choice of whether you want recursive semantics or non-recursive semantics. If you know you're never going to have to deal with reentrancy and recursion, then you can use the non-recursive implementations, which are really, really fast because they've devolved into basically hardware instructions. Let's talk about some of the key methods in ReentrantLock. So once again, these are very similar to what we saw with semaphore, just the names are somewhat different. Rather than acquire and release, we have lock and unlock. These methods are all defined in the lock interface. So if you take a look at the interface of lock, you'll see those methods we just looked at here. And as you can see, all these methods simply forward to the underlying sync hierarchy, which comes from the abstract queued synchronizer framework. So you're leveraging all that code that's already there. Lock is very simple. It simply acquires a lock if there's one available, if it's not locked. Now, if the lock isn't available, the behavior of the lock implementation in the abstract queued synchronizer class depends on the fairness policy. And so if it's a fair lock, then it will go ahead and sleep and go to the end of the queue. If it's an unfair lock, it may spin for a bit to try to get access to something. So it sort of depends on what policy is set as to what the behavior is going to be. In general, non-fair implementations are optimized in hardware, and they can do things like use spin locks or other things to try to lock for brief periods of time. But the fair implementations park themselves immediately on a wait queue. Lock interruptibly acquires a lock unless it's interrupted. We saw how to interrupt things before when we talked about the Java thread lifecycle. In contrast, lock is not interruptible, so that makes it more like a synchronized statement or synchronized method. Try-lock acquires the lock only if it's not already held when you invoke it. And like semaphores, the untimed version of try-lock ignores the fairness setting altogether and can barge. So be aware of that. Unlock attempts to release the lock. Now, why does it attempt to release the lock? Unlike semaphores, where the thread that acquires the semaphore does not have to be the one that releases it, in the case of a ReentrantLock, the thread that acquires it must be the one to release it. And if that's not the case, then an exception will be thrown. So if one thread acquires a lock and then another thread comes along and unlocks that lock, then an exception will be thrown. And that's because a reentrant lock is intended to be used in a fully bracketed manner. So that would be a protocol violation if you had different threads would release it.
Is it going to unlock before it throws the exception?
I believe at that point the behavior is undefined. That's a good thing to look into, though. If you have code that is doing that, I'm actually not sure off the top of my head what the behavior will be, but it's something that would be worth looking into. I'm sure that the documentation says. There's a number of other reentrant lock methods. Many of them, we're just going to talk about a few of them. Notice that these methods are what go above and beyond what's available in Java's synchronized statements and methods. So we have things like try lock, which is a timed lock, which does honor fairness and can't barge. It'll wait up to that amount of time to try to get the lock. Is fair returns true if the lock has a fairness setting set to true. Is locked returns true if the lock is currently held. The only downside with this is it's a bit non-deterministic, because by the time it returns to you, whether it's true or false, somebody else might have come along, or things may have changed in the meantime, and someone else may have grabbed the lock. So just be aware of that. There's also a method called newCondition, which returns a condition for use with the lock's instance. And we'll talk more about this when we talk about condition objects later, but that's the way it's created by a factory method. When we talk about Java condition objects, we'll discuss this in more detail. OK, so that's the end of part 2 of this lesson. So here's part 3 of the Java ReentrantLock discussion. Here we'll talk about how to use a reentrant lock in Java programs. So I'm going to give you an example, and the example we're going to look at is the ArrayBlockingQueue class, which you can get if you go to this link and read about it. And it provides a so-called blocking bounded FIFO queue. What the heck does that mean? Well, if we look at a couple other things that are part of this class, it'll make a little bit more sense. So ArrayBlockingQueue extends abstract queue, which provides some of the implementation details for the queue. And it implements an interface called BlockingQueue. And the BlockingQueue defines a bunch of methods that are used for blocking. So blocking means if the queue is empty, you wait to take something from it. If the queue is full, you wait to put something into it. So that's what a BlockingQueue means. And bounded BlockingQueue simply means that it doesn't grow without bound. There's a limit to how big it will be, although you could make it astronomically big if you wanted to. And FIFO simply means first in, first out. So the order in which things are removed or the order in which they're put in. So other things like priorities don't matter. It's just the order. So it's just a queue that can be used to block. There's obviously a couple different parts. There's the interface part, which is what you would typically see as a programmer. But we're going to actually look under the hood, and we're going to talk about some of the implementation details that you don't normally see. So if you were to peek inside the implementation of ArrayBlockingQueue, you would see a bunch of things. And this is just a subset of them. We'll talk about more of them later. And we're going to use a reentrant lock, or Java uses a reentrant lock. This is what you get with Java. This is not my invention. This is from the Java class library. It uses a reentrant lock in lieu of Java's built-in monitor objects. And it does that because of the various limitations with monitor objects. Yes, sir?
So how do you know if it's fair or non-fair here?
How do we know if it's fair or unfair? We look at the implementation, which comes up in a slide or two. So we look and see how this is initialized. So you can see that we have a reentrant lock, and this will then be used to protect the state, right? So the number of items in the blocking queue, the indices for adding and removing items, and the number of elements that are currently in the queue, which is the count. Note that because we use a reentrant lock, these fields do not have to be defined as volatile, because they're going to be protected by a lock. They really wouldn't work even if they were volatile, by the way, because of other things. But the reentrant lock handles all the atomicity and visibility issues, as we've talked about before. All right, so let's take a look. And I'm going to try to visualize the code here by this little monitor diagram that we're going to see. You'll see this a lot as we talk about the synchronizers, because it helps give you a view of how things work. So we start out, the lock is unlocked, and the hold count is 0. And then some thread comes along, thread T1, and it tries to take an element from an empty queue. So we've got a queue that can have up to 10 elements. We try to take an element. The queue is empty. Here's what happens. So we come in to the implementation here, and you can see that we're going to go ahead and lock interruptibly. So we're going to get ourselves a reentrant lock, and we're going to go ahead and lock interruptibly. Oh, and going back to your earlier question, because I don't think I have it here, when you take a look at this, when we look at the constructor, it'll say lock equal new reentrant lock, and it doesn't say true. It just gives the default version. So by default, it's non-fair. And we don't need it to be fair for this case. So because it's not, the queue is what's being used to order things, not the lock. So we go ahead and acquire the lock, and now we're in the locked state, and the hold count is 1 because we've acquired the lock. Now let's say another thread comes along. This is thread T2. It also calls take, but notice that this guy's currently locked. So what will happen here is that this thread T2, let's say he's going to end up with the unlock operation getting called. He's going to call unlock. And in that case, we're going to transition back from being locked to being unlocked. So when unlock gets called, that's going to transition it back. So now the hold count is back to 0. And notice the use of the try finally block, which is just a good habit to get into. Now, we will talk later about what happens when you are doing these various loops. This gets us into a different topic, which is outside the scope of ReentrantLock, but this is going to be used when we're going to have to wait if the queue is empty, as is shown in this particular case. And so what you can see here is that while the count equals 0, we're going to wait. And notice that this check is always made, this count equals 0 check is always made with the lock held. When a wait is called, it will atomically put the calling thread to sleep and unlock the lock. But we'll talk about that when we get into discussing the condition objects. You can also read more about this in the monitor object pattern, where you can find as a link here that describes that. Yes, Anne?
Is that all one thread?
So just different threads, some of which doing take, some of which are doing the other things.
Are the locks and unlocks bracketed?
Yes, yes. For ReentrantLocks, locks and unlocks are always bracketed, yes. OK, so that is the end of part 3. We have a short time to